everyone. Now we will take you on a journey to Japan. We would like to give you a glimpse into the construction industry and the digital transformation of the manufacturing market. So welcome to next generation of LGS manufacturing. My name is Stephanie Bay. Here we have our team. We have a global team of 5 team members from Japan, China, Poland, and Germany, and we are all joining this call today. Let's take a brief look at the agenda. So today we would like to give you a general idea of the challenges that we face in this industry. We would like to show you how we would like to overcome those challenges. We will provide some solutions and show you some projects that we are currently working on. Then we will conclude by showing you our future roadmap. Let's get started. Nohara is a manufacturer and reseller of construction material. We sell LGS profiles, plaster boards. We're actually the biggest reseller of plaster boards in Japan. Nohara is a family business, started 1598. Yes, you heard correctly. And that is also impressive about Japan because you can actually meet construction companies with such a history. Nohara has also formed a capital alliance together with Swedish BIM Object. So we are working for the digital construction department within Nohara, our team, and we provide services within BIM, consulting, 5D cost estimation, and digital twin solutions together with our partner SimLab. A video I'm showing you right now is our latest project together with our partner SimLab, and we're showing you here Okupo Hospital, which is displayed in the Stages app from SimLab. What you can see here is a Matterboard 3D walkthrough we use the Pro 2 camera to scan the hospital. We went there 3 times and did 3 stages of scanning. And of course, we tagged all the Matter tags here with information for our MEP contractor for, medical gas, ventilation system, and doors. All the construction material that we provided for them. So let's have a look at the current stage of construction. What I'm showing you here is no groundbreaking news. You've seen it all. You've heard it all before. The construction business has generally been considered a traditional industry with limited appetite for innovation. We all know that. The economic sector with the lowest productivity gains actually, but we are all participating on this event to change that, right? We also think that companies like Nohara that are manufacturing and reselling materials can make a change because construction materials are closely related to productivity. They can have significant impact on labor costs as well as on the quality and sustainability of the assets. And let's not forget, there is a huge potential. When you take a look at the top 100 global construction companies, you will realize that 15 companies are from Japan. So there's a huge potential. So what are the challenges in our industry? There are some specialties to Japan. And when it comes to Japan, you probably heard of the chronic labor shortage that is caused by the nation's shrinking working age population. Also, what is special to Japan is natural disasters. There is, for instance, the Pacific Ring of Fire. And that area is just around Japan in that region. And it happens to be that area where 80% of the largest earthquakes happen. So basically a pretty, dangerous place to live. So what are the external industry challenges that Nohara is facing? So let me give you an example of the current estimation process. Let me paint you a picture of how it looks right now. So a subcontractor will receive a bill of quantity from a general contractor, and this subcontractor is an interior contractor for LGS profiles and partition walls. So he will receive this BOQ probably in an Excel file or PDF format and some 2D drawings in PDF. The line items in the BOQ will probably be like total amounts. Maybe if he's lucky, there are some amounts per room, but he basically has no clue where those quantities are. So if this subcontractor has time, and those guys are usually quite busy, he will take a look at the 2D drawings and tries to figure out where those quantities are. So I can tell you it's a very lengthy estimation process which requires a lot of manual work. This would take him probably 1 week, 2 weeks. Then he will contact Nohara because we are the reseller of this material. We will also take a look at the quantities and make a quote for the subcontractor. Then he will wrap it up at, labor costs, equipment costs. He will add a profit and make a quote for the general contractor. And this estimation process probably takes 1 month. And we say, let's make it shorter. Let's switch to BIM. Also, I would like to tell you about the internal industry challenges that Nohara is facing, because let's not forget the legacy of the current business model. And the current business model is all about making labor costs and consumption rates as gray and complex as possible. And let's not forget that those guys, the subcontractors, are our actual customers. So what we are proposing is kind of a disruption of their current business model. And that is why it is very important that we get everyone on board, the subcontractor, the general contractor, when we do BIM. So what are the tools that we are using? Well, we're using Excel. It's common file used in Japan. Revit. It's gaining more and more ground in Japan. And then, of course, we can interface those data with international formats like IFC, and we can add on Power BI for the visuals. So here is our workflow proposal. I told you before, we want to switch to BIM. So what we're currently doing is we will receive an LOD 300 BIM model from the general contractor. We will enrich the data and create visual formats for the subcontractor. And here we can provide all those quantities the subcontractor needs. Because when we're using BIM, we can extract quantity by room, by floor level, by wall type. You name it, it's BIM. We can extract all the data we're interested in. Then we can match the models with real-world scans to ensure CNC machines receive accurate data for cutting parts needed for site delivery. So this is the rough workflow of our proposal. And now I will hand over to my colleague Adam Piaskowski, and he will explain to you how this work proposal looks more detailed.
Thank you, Stephanie, for the context. Thank you very much for the timeline of our presentation. And I'm just going to jump in straight to model validation. So in order to validate the models, and are actually even just to highlight what is the biggest obstacle when we do costing or when we do detail enrichment, and that is the quality of the models. Because that's such a big obstacle, and that's something that will basically, it's like a foundation for everything else. So if we get this wrong, everything else is going to have problems. And to ensure that the foundation is correct, we need to share what is part of our process with the rest of the team so that they can incorporate our considerations into their workflows. And to do that, the easiest way is to create some kind of a guideline which we can easily explain and which the rest of the team that is involved in the model creation can help them understand how to set up this file so that it is reduced of most of the errors. And just to show you a couple of common errors that we have in the models, I should first refer to a method for validating those errors. So of course, every model has warnings, Revit warnings. And usually it's a common practice to ignore them because Revit tells you can ignore them. So why would you not ignore them? And then often there are problems which you can't resolve. For example, part of the frame somewhere inside of the door family is going through a wall, and you know that this is the size of the door and this is the size of the corridor, and you want to have this way, but maybe there's something wrong inside this door family that is actually making that clash. And maybe later when we take quantities and we check the area of this door, it is actually, reasonable that this error is showing up. Maybe there's a floor that is clashing with another floor, and that usually again creates some kind of an overlap, and it increases the area or just shows inaccuracy in those areas. Maybe there's two walls that are one overlapping the other, or maybe a wall is slightly off axis, and then when we try to generate geometry inside of that wall, all of these generated geometries will have wrong reference point, and they will be all slightly skewed. So we do have tools where we can check what kind of error this is and what kind of warning message it gives. And we can also highlight using Dynamo what kind of errors are where. And this is a little bit easier to troubleshoot than from troubleshooting the Revit warnings, because Revit warnings just gives you a general list, and then you have to press on each warning and it will tell you where that warning is located, and it can be a very lengthy process. If you could have like an overall visual and see where are the problems in the model, I think that's a little bit easier to digest, and also to just, without using the warning editor, you could basically just press on those elements and fix those warnings on the fly. But there are also warnings which are not very visible or not even highlighted by the warning script. For example, when we generate finishes, sometimes the door geometries, they're perfectly fine. They're cutting the void through the first wall, but maybe they're not cutting voids outside of that first wall. So maybe if we add a couple of millimeters of baseboard, this baseboard is not going to be cut because the void of the door is not long enough. There are also other errors which are actually very easy to make. I don't know if you guys ever tried inside of Revit trying to join 3-4 walls of different type, of different thickness, where maybe their layers are slightly offset, which is maybe the way that it should be, but Revit doesn't want to really accept that. And sometimes there's a small omission, and for example, a wall goes over a bit longer over the connection, and then basically once we want to generate this wall, it will take each one of those walls as separate elements, and that little partition part of the wall with the wrong wall type will be framed as the wrong wall type and will give us inaccuracies again. And then lastly, we have classification. It's a common standard to use different classifications. In our case, we are mostly looking into Uniclass, which is very popular right now in Japan. Before that, we were using master format. I know that there are many other standards in Europe and in Australia and New Zealand and the US and so on. We can actually assign any of these classifications. However, they all kind of lack certain components. They lack certain precision at our level of manufacturing. So they are more general. They are more general for systems. They are more general for products. However, they're not, or they often don't have the distinction between the same product family, but different maybe thicknesses of those product families. Or maybe systems which have different spans between the studs, in our case for steel structures. So we are creating our own classification code which can accept any kind of differentiation between that we want to achieve, and we just basically go with a code. We go with the most obvious part, which is our standard classification material code. Then we add the layer thickness, then we can add stud information, then we can add insulation, then we can add the stud profile, and so on and so on. So we can very accurately specify what kind of information should go into these. And then we can, of course, link other classification codes, and often we see that there is a repetition. So it's the same classification code for our different codes, And that clearly shows that we don't have enough distinction to cost these elements using the standard classifications. Once we've validated the model, we can enrich the data that it has. So the level of development is split into level of detail and level of information. So we add geometry at different levels of detail. So we can generate some geometry, which is like basic geometry, like those baseboards or floor finishes, etc. That's what we call LOD 300. It might vary the classification again, depending on to which standard you're following. And then at LOD 400, that's where we add a more detailed information. That's when we generate specific plaster boards, when we generate steel profiles, screws, connections, etc. And then we also add data to those elements, both at LOD 300 and 400. And that's where we add information about the location of those elements, the waste estimation, the parameters that are distinguishing projects and families, and also how we can choose those projects and families that are a composition inside of our model. So there are different levels of development, and basically it goes from lower level of detail to a higher level of detail. And in our case, for example, if we enrich a level of detail for a wall, we're starting with just a generic wall. We add layer information to this, and then we split it into parts. And then each of these layers is a separate part. And then we use AECH, which is a software for detailing, to actually split those parts, split those layers into smaller parts and horizontal and vertical grids, which divide our plasterboards with some rule-based schemas. They replace wall layers and place steel studs inside of those layers. So this is how we add information to geometry from data. So for example, we can generate finishes and we can generate baseboards. And here you can see, for example, how we generated this paint layer, which is separate from the main wall. And we can also frame the main walls, select just these main walls separately. So we can also cost these layers separately. And the importance here is that we can have a structural wall that goes between many rooms and then have finishes that are dependent for each room. So it's nice, this division there. We can also create assemblies from these, so we can choose certain elements that we want to use for assembly. We can number those elements and we can place them on sheets. And here you can see we can also dimension them and create shop-ready drawings for that. So we also enrich data when it comes to families. So for example, Nohara is a manufacturer of doors, and to manually cost specific doors, I mean, we're not talking about just doors that you could install in your home and they have a handle and a leaf and maybe a lock. We're talking about doors for hospitals, which often have, mechanisms for fire prevention. They are actually sliding. They have special acoustic properties, pneumatic opening, and so on. So they are very complex door families, which take a long time to cost manually, because they can all be different. They can have different dimensions, different materials that are, composing them, different frames, etc. And it takes as long as 2 weeks to cost one type of doors for, or maybe one project with different doors for a client. And 2 weeks later, that information might be no longer relevant. So we try to make a system which will enable costing those families and those doors, for example, and choosing them, specifying them as we go. So we have a drop-down list. We choose all the components. They are all costed. They are all connected with a classification code, and they can very easily be basically assembled together. And the price is a bit like specifying a car purchase online. We also enrich data by adding waste information. So we can basically use bin packing algorithms thanks to miscellany package in Dynamo. And basically what we can do with this is we can cut our plasterboards into parts and estimate which parts can be reused in which room. And the bigger the project, or rather the bigger the area that the same plasterboard can be applied, usually the lesser the waste. So we can optimize that waste quite considerably by using offcuts in different locations. And then we can apply QR codes to those plasterboards to know where that element could go as an offcut. So we know, or rather somebody that installs the board on site will know that this plasterboard has its use application in those rooms. And if there's an offcut from this plasterboard, that's where it should be located. Of course, there are some limitations to this. You're probably not going to move a plasterboard from first floor to the other end of the building on the fourth floor, because it's just the logistics of moving that plasterboard might be more expensive than the actual plasterboard. But if you can safely use an area which is optimal for moving that plasterboard and reuse that material, well, then it's not just the cost that's optimized, but it's also the waste and the care for our environment. We then merge this data. So we take the product information and we take the geometry information and the location information that was added to this geometry information, and we combine it all together and give a meaningful report to executive viewing, so that we can have the cost report, we can have a 3D model annotated with this information on top, and we can have variable cost models. So if, for example, we can compare options, we can change layouts, we can change setups, change materials, and very easily see how rather the choices the designers make can affect the cost. And the way we map this data is by using Python and Dynamo, and we basically use classification codes to map the database with the geometry in Revit, and we export this into new data files. So here's a video of how this process works, along with the enrichment of data. So as you can see here, we have a model which is divided already into plasterboards and framing. However, we're just going to create this from the start. So here's a couple of walls with a door inside, and as you can see, AECH is doing its magic, and it's splitting the walls into plasterboards and frames. And then we are actually adding information to those plasterboards. So right now we're adding the classification code, and then we are adding other information such as room ID and location and the parts ID, so that we can recognize where those elements are. We are then adding QR codes, and you can see here that the QR codes can be checked on each element, and scanning your phone could give you the information that's contained within the QR code. And then the elements are ready for export. So here we can just load this information to Power BI, and we can show you some simple graphs, how we can filter this data and show you what kind of costs are associated with this data in there. So there are also different cost factors which are influencing the final cost, and that could be, for example, openings. We need to put extra reinforcement around openings if we are not having this done already by LOD 400 model. But if we're looking at LOD 300, we don't have the accurate geometry of every steel frame. So we create some assumptions for where that steel frame could be more expensive. We can also look at installation complexity. So if we have a column, it's probably going to take a significant more time per square meter than it would be if it was a flat wall. The same with openings. So we can actually use algorithms to derive where these occurrences exist in the model, and we can apply factors which are going to factor in the costs. And that can also work for productivity ratios and price development. So for example, if we only have so few of this material in the model, its unit price is going to be significantly higher than if we had, I don't know, 10,000 square meters of this material, because of course the economies of scale influence the cost. So here it's a small kind of excerpt from a costing report. You can see, for example, here how we can optimize the construction waste. And if we use just a standard assumption that for plasterboards our waste is at around 15%, actually it's very generous 15%, because it can go up to 30-35% according to the British standards. And we can optimize this by reducing those to around 9% for this particular case. It is again very case dependent, and you can see that the bigger the area, the lesser the waste, and the smaller the area, the higher the waste. So it also depends on the size of our building and on the reusability of a certain material type. So just to sum it all up, this section, we can reduce waste, we can reduce manual errors, because the errors that can really happen are only at the beginning when we validate the model. And there could be errors in the way that we do calculations, or there could be approximation errors. However, they are very easily looked into, because this is basically just like a sheet with, different kind of factors and different kind of multipliers and a cost database, which is, let's say, has a few hundred entries. And then from that, we can generate thousands of individual price points for each element, which is much easier to, which we can later filter. And it's much easier to find errors, if there are any to be, rather than if this was a manual calculation, which was performed by a single individual or a group, which had a certain way of doing it, and communicating that method would be more difficult to somebody that would validate this. There is, of course, an entire reduction in errors based on that it's a computer that does the calculations, so the human error is also omitted, beyond just having the wrong price point or a wrong factor. And also it's very dynamic. So if we change the model, if we change something in the model setup, it's easy to recalculate that change following the change update. However, this is not a magic bullet. So the setup is quite a lengthy process to set up the generating software properly, to set up the databases, to set up the classifications, set up the workflow kind of order, families that enable this parametric design. It is considerably lengthy process, and of course the accuracy greatly depends on the model that we receive. So there's no 100% assurance that this is actually going to be the cost. There are also some theories that the closer you look into something, the bigger your error margin could be. However, I believe that using prediction, kind of cost prediction, which is detailed, is actually a better method than just doing guesswork or manual calculations. But there's another, should I say, difficulty stemming from the heaviness of the models. So if we want to assess LOD 400 models, these are very geometry heavy, and to even generate this geometry, you need a lot of computing power to process all of this. Let me just share the floor with my colleague, Henry. Thank you.
Thanks, Adam. So now I'm going to talk about the idea and concept we are exploring and doing the research about, which is how to do the validation and comparison, or even auto-generation between the scan data and BIM model. As we all know, there are basically two directions or two concepts. The first one is regarding the existing building. We need to generate the BIM model on top of the existing conditions using either laser scan or some other tools to do that. The other way around is to have the new project. We need to keep updating the BIM model so that it can match the existing as-built conditions. And for renovation projects used with the existing building, the most used tool is to do the laser scan, and we generate BIM model using the scan data as the basic or foundation. And for the ongoing construction, we do the laser scan or some other scan. We can have the as-built model so that we can do the BIM model validation against that. There are some tools or softwares we are doing the research about. So here is just two examples. The first one is Cinto. So what they do is they can do the conversion between the laser scan and the digital twin. It's a middleware. We can import the digital twin laser scan data, and they can do the validation of that so that it can support our generation, either generation of BIM model, or it can compare with the BIM model so that we can find certain mismatch places. Of course, the software is keep updating, and they may have so many new functions we do not know of. So this is just one explanation of this software. And another example we are exploring is the tool called ClearEdge 3D. As you can see from the snapshot, it is more like Naviswork user interface. So what they do is they can import both the digital twin data and the BIM model altogether. Just like we do the clash detection, they can detect, okay, this part there's mismatch, and this part there's certain missing part either in the BIM model or the digital twin data. So and on top of that, they have this really smart algorithm. They can auto-detect certain objects, whether this is a door, a window, a floor, a column, or a BIM, so that it can somehow help us to do the generation or updating the BIM model. Of course, the software is not perfect. You know, there are certain parts, there's stupid mistakes, so it's not perfect. But anyway, what we are trying to explore right now is, you know, either there's a certain tool or certain best practice, we can do a much more efficient and smart way to do the validation or even auto-generation from the digital twin model to the BIM model. So this is what we are trying to explore. Of course, we want to reach out to our audience. If you have certain new ideas or, you know, existing practice, feel free to contact us. Your suggestions and ideas are so welcome. Okay, so that's pretty much of my part. I will hand over to my colleague. Thanks for your attention. Now my colleague David will be talking about NPITA manufacturing. Thank you.
Thank you, Henry-san, for introduction. I would like to now show you how our team used the process mentioned above to create one of the core products, which is NPITA. Based on the architect's model, we make the precise element parts so we can make a proper cost estimation and also the prefabrication drawings. So, but actually, what is NPITA product? So, it's a indirect unit for lighting, which can be installed on simple ceiling constructions. So, we wanted to create a precise BIM content model with manufacturer data and ready for prefabrication. To do that, we use Revit software to create LOD 300 models and the Dynamo to create the LOD 400 and making it more customizable. We used data shapes to create kind of user interface that we can configure the profiles with all for the whole dimensions. So let me guide you now through how an NPITA model is created actually. So for LOD 300 we use wall system families to just insert NPITA profile type as a sweep, and by using the Dynamo script we are changing profile dimension to prepare it for 400 model. So as I mentioned before, we're using user interface from data shape, so we can change the plasterboard thickness and profile depth. And this simple model can be used by architects for lighting visualization, for example. And after that, we're using AECH tool to create the proper LOD 400 model with stats, plates, and covers, so you can make a precise cost estimations. And in the end, we create assembly with all these parts, and Dynamo scripts help us to make it automated dimensions and tagging. With fully detailed drawings, then we can easily automate the process of manufacturing. Instructions and the drawings can be easily used for CNC machines, and that's how we're exactly doing right now. So, but in the future, we plan to create manuals using augmented reality models to fully recycle the available technologies. By using QR code, for example, we could locate elements in the construction site from the model. Unfortunately, for now, we still have to wait for augmented reality hardware to become more practical and wide used. Well, that's it. Thank you for listening and giving back voice to Stephanie.
So we've come to the end of our presentation. We've showed you our current state of affairs. We explained to you how we want to disrupt the current business model by making pricing more transparent and automating cost estimation processes. We talked about model validation and the importance of high-quality BIM models. We talked about our research on scan to BIM, and we showed you how we can automate framing with AECH, create assemblies, and add QR codes with Dynamo. We also talked about waste reduction today, And please let me remind you, this is coming from a manufacturer. Our business is to have high volume sales. But still, we think that this is the right approach, because if we want to change the game, we need to adapt as well. And also we are convinced that by providing those solutions, we can set us apart from our competitors, and eventually this will lead us to more customers. So let's take a look at the last slide. Here we have our development guideline. And regarding our roadmap, we have ongoing challenges like improving better ways for model checking. In the longer future, we want to export models and data into formats such as IFC or COBie. Also, we want to work with Nohara on semantic web and graph databases so we can combine products, users, processes, just to name a few of them, and of course our historical cost data. So if that is something of interest for you, please do contact us. Like Henry also mentioned, any ideas, input, you're very welcome. We are open for collaborations, even new team members. So please don't be shy. You've seen our QR codes here in the presentation. We are all on LinkedIn. We speak several languages, so I think regarding the communication, we can work that part out. So I guess we're ready for your questions now. And before that, I would like to thank our team, Adam, Henry, David. Thank you so much for today's presentation, and of course our team leader, Jun Inoue-san from Nohara, who made this team happen. Last not but least, I want of course to thank the audience. Thank you so much for your patience and for your attention. We showed you tons of stuff today. We hope you liked it, you enjoyed it. So please enjoy the rest of the hackathon. Reach out. See you soon.